Calculations, Analysis, and Conclusion. The spring constant will be found using both an algebraic and a graphical approach. To find the spring constant algebraically, we start with our formula for the period, and we want to get rid of that square root sign. So what do? Square both sides. So we get t squared is 4 pi squared, that's 2 pi squared, and then you square a radical, you just get what was inside, so that's m over k, and then rearrange that to solve for k. So k is 4 pi squared times the mass divided by the period squared of that oscillation for that particular mass. Using the sample data below, calculate the period and the spring constant. Note that the masses are listed in grams, and you'll have to convert that to kilograms. So please pause this, give it a shot, and when you're ready, move to the next slide for the answer. And again, convert this to kilograms. So let's see, 60 grams would be what? 0.060 kilograms. So it was easy to find the period, I would imagine. Just divide this number by 10 and then round it off to 2 decimal places, 2 sig figs here. And then the spring constant, use that formula from a few slides back and make sure you converted the grams to kilograms. And look at this, pretty constant. Spring constant looks pretty constant across the different masses. Now it's time to see how we do it using a graphical approach. We start again with the period. We square both sides to get rid of the radical. Now this time we're going to want k in the numerator, and we'll have it as a function of mass. So do you think you see where we're going with this yet? Right here's the clue. And we'll move to the next slide and show you what we're up to. This, which we found on the previous slide, is in the same format as the slope-intercept equation. And let's see, what do we have? We have b is equal to 0, so the y-intercept is 0 here. M would be on the y-axis. T squared, not t. We can actually plot t squared on the x-axis. So what is this going to be now? That's going to be the slope of the line, y equals mx plus b. So the slope is equal to k over 4 pi squared, and since we want to find k, we multiply the slope by 4 pi squared, and then we get k. Plotting the mass on the y-axis and t squared on the x-axis indicates that the y-intercept should be 0, right? b equals 0 from the slope-intercept equation. Physically, that also makes sense, for if you don't attach a mass, the spring will not oscillate, so there will be no period. So b matches that term there, which is 0. When you plot your data, though, you may not find that a line of best fit intersects the point 0, 0. A perfect spring would certainly do so, but friction in the spring may require a minimum attached mass before it starts oscillating. There's no perfect answer for whether you should plot 0, 0, so this is really up to the teacher's discretion. Just make it clear ahead of time what you'd like the students to do. Some practice. Please plot the graph of m, mass, which is now in kilograms, versus t squared. Draw the line of best fit and find the slope. Ensure you label both axes with their title and also the units. So pause the video, give that a shot, and come on back when you're ready to the next slide. Your graph should look something like the graph here, and let's see if the line of best fit makes sense. Well, we have 1 point below the line, and we have 2 above it, and they kind of look right because this guy here is almost on the line, so that's a pretty good line. And this one actually does go through the origin. So we pick a point that intersects some grid lines so we can be pretty sure that's a good number, and that's 0.08, 0.11. So when we find the slope, we do, where's our slope? Here we are, rise over run, 0.11 minus 0, and then 0.08 minus 0. And that gives us a slope of 1.375. That is not k, though. And let me just point one more thing out. This is correctly labeled t squared. The units are seconds squared. Mass is in kilograms. Our slope is equal to k over 4 pi squared. So when we multiply both sides by 4 pi squared, 4 pi squared here, This cancels this, and the slope is equal to, k is equal to 4 pi squared times the slope. Put that in, and we find that k is 54.2 newtons per meter, which was very close to the value found algebraically. The advantage of the graphing approach is it smooths out the data from all the points. Depending on the springs available, the students may have springs with the same spring constant. In this case, the class can compare their results. Sometimes you can purchase springs with known spring constants. In this case, they could do a percent error calculation between the known value and the value they found in the lab. If you have a set of springs where some are stretched out and you have some extra time, have a group or groups of students use those springs and compare the results to a group using a good spring. The results shown here with the red line represent a nonlinear relationship between m and t squared, between the mass and t squared. The line of best fit, which you can get with a program, does not fit the points very well. This spring, with the red here, is not described by Hooke's law.